Hey guys, so this is chapter 2, section 1. It's the first in a two-part video about matter and atoms. We went over in class this week, and for anyone who missed it or wants to see it again. So, what are things made of? That's the big question that we're trying to ask here. What is the world made of around us? There's a lot of stuff out there. When you stop to think about the number of different substances in the world, just in this picture of a classroom, you've got the brick that makes up the walls and whatever the covering on that is, whether it's paint or some kind of cloth it looks like. You got plastic posters and the paper that's in them and the ink that's printed on them, and this podium is made out of some kind of press board, and there's metal hinges and rubber borders, and there's the floor and the air in the room, and who knows what kind of chemicals are inside this projector, little metal circuits and things. And you've got the wind and the air outside, and the trees and their leaves and the stems and the grass, and I mean there's trillions of different things in the world. There's so much stuff. And there's so many different kinds of everything. So what is it all made of? It turns out not that much stuff. There's not really that many things it's made of. You and this plant and the coal and the wood tree here and even the cellophane that these things are wrapped in are all mostly made out of carbon. The stuff that we're made out of is called matter. Matter is anything that has mass and takes up space. So, I mean, everything from this cup to a marker to the computer I'm working on, all of it has mass and takes up space. It's got a certain amount of volume that it takes. Chemistry can tell us how we can take one kind of matter and change it into a totally new kind of matter. For instance, how did I change this tree into charcoal? So there's a number of terms we have to learn. And the first one is going to be substance. And I already said that actually on the last slide. On the first slide is how many substances can you identify? A substance is a very specific term. And it's a kind of matter that can't be separated into other substances by physical means. Things like heating it up or cooling it off or filtering it or drying it or sorting it or dissolving it. No matter what I do to that corn oil, it's always going to be corn oil. And the image I try to use whenever I teach this is a magic pair of tongs. If I could take some magic tweezers in there and reach all the way in and grab one molecule out of that corn oil, what kind of molecule is it going to be? If it's going to be the same thing every time, then it's a pure substance. Corn oil is just corn oil. Every atom in there, every molecule in there is going to be a corn oil molecule. It won't do me any good to filter this. It's still going to be corn oil. Oil and vinegar dressing is a mixture. A mixture is matter that contains more than one substance. Anyone who has Italian dressing in the refrigerator knows you have to shake it before you use it because the oil and vinegar separate. If I took that same pair of tweezers and tried to pull out a molecule, who knows what I'd get? Would I get all of the oil? Would I get the vinegar? Would I get one of the little seeds in the bottom? So a mixture is just something that contains more than one substance. Orange juice is an example of a mixture. Even though it might say pure on the bottle, in science we have very specific meanings for those words. So even though it says pure orange juice on the bottle, it's not really a pure substance. If I took those tweezers and reached in, I might get water, or I might get some sort of a flavoring, or citric acid, or sugars, or even a piece of pulp if you buy your orange juice with pulp in it. But I like this graphic here. I think it puts it well. A substance is the same all the way through. But a mixture is a bunch of different substances mixed together. So when we look around the world, take a second to look around. What is your desk or your table or whatever you're working on made of? Is it made of wood, metal, glass? And then can you think of any physical properties? Things like, is it heavy or is it bendable? Does it feel cold? Can you scratch it? My desk is made out of pressboard, which is like wood pulp with glue, and it's pretty heavy. I've tried to pick it up; it's pretty heavy. I've moved it a couple of times. Is it bendable? I mean, a little bit. If I lean on it, it definitely warps a little in the middle. It's not a very good desk. Does it feel cold? Yeah, it does. It doesn't really hold on to heat very well. And I can scratch it. It's all scratched up. It's very old, and even just moving my mouse around on it has left a big patch of scratched up desktop. So those are some physical properties. Physical properties are things that can be measured or seen through direct observation. I don't have to do anything to my desk to figure out that it's heavy or that it's shaped the way it is or the color that it is. Those are all things I can just observe and see. Things like, for instance, the mass of an object. I can just measure that. I can just weigh this thing and I can tell you how much it weighs. I can tell you how much mass it has. I know wood floats because I can just put it on water and it floats and I can see it directly. Gold is good for jewelry because it bends real easy. I can bend gold around your finger and make a gold ring, but I can't bend glass. Glass tends to shatter. Just ask any of your smartphones. Physical changes are any changes to those physical properties. Things that include things like melting this, the shape of all of this aluminum scrap gets melted down and reshaped into this sculpture. I haven't changed the molecules or the atoms that are in there at all. I've just changed their shape. I've melted them into a liquid, made them solid again, and then bent them into the shape I want. I haven't changed it chemically. It's still aluminum. This snowman here is made out of water and a top hat and some coal and a carrot. He's just frozen. As the sun comes up and he gets warm, he starts to turn into liquid water. I still have all the same molecules. All the water is still there. It's just in a liquid phase now instead of a solid phase. There's still a carrot nose. There's still all the coal, and the hat. I still have all the same matter. It's just changed shape. So that's important. Physical changes can include changes in shape, phase, or temperature. By phase, we mean solid, liquid, and gas. So physical changes include heating, cooling, melting, freezing, boiling, dissolving, like putting sugar in water. If you put your sugar into your coffee or into your water, the molecules separate from each other and they go into solution, but the sugar's still there. When I drink the water, it still tastes like sugar. Bending something or evaporating something or tearing a piece of paper or, any of those kinds of changes that don't change what it's made of. If I rip a sheet of paper in half, I still have paper. Chemical properties, on the other hand, are observed when a substance changes into a different substance. In order to measure a chemical property, I have to actually change the matter. I can't just look at something and determine if it's flammable or not, for instance. I tear a piece of paper in half, that's a physical change. It's two pieces of paper. But if I take those two same pieces of paper and I want to know if they burn, I can't tell that just by looking at it. I have to light it on fire to determine if it's flammable. That's a chemical property. The example here is rust. Rust results from a chemical change. Iron, in the presence of oxygen and water, will rust. It goes from being iron to becoming iron oxide. It's a different compound now. Iron is hard. It's very rigid. It maintains its shape. Rust is soft and flaky. I can pick it off with my fingers. It's very breaking. It's like very crumbly, very brittle. So there are some signs that a chemical change has occurred. Bubbling would be the first one. If you've ever put vinegar and baking soda together, you know that they bubble up because a new gas is being formed. a temperature change. So you've probably used an instant ice pack before. You have a plastic bag and inside is another plastic bag, and you hit it hard enough to break that inside bag, and then the two chemicals mix together and it gets very cold. Or one of those heat packs that you rip open and they get very hot for like 8 hours. Those are an indication that a chemical change has happened. It could turn cloudy, like when a new solid is forming. You mix two things together and they create a new solid. Or a color change, like a glow stick. You crack a glow stick open and you shake it up and the two chemicals get together and they make a new color. For those sorts of changes, I know that a new compound has been created. And then a note on scale. Macroscopic is large sizes, right? Things that are big. Macroscopic are the things I use in my life, like my cup and my pen and anything around me that is the large size scale. Microscopic scales are very tiny scales. And when we talk about atoms, we're talking about the tiniest possible scale. So think of this desert at 100 meters across, and then a handful of sand at 10 centimeters across. And then we zoom into just 1 millimeter across, and you can see the individual grains of sand. If we could take one tiny grain of sand, there are 200 million atoms in it. That's a 2 and 20 zeros. Take a second to appreciate that. 200 million atoms in a single grain of sand. When we talk about atoms, they are as small as the universe is big. We just finished talking about how big the universe is, how unfathomably large it is. Well, now we're going to reverse that, and we're going to look at how unimaginably small the world of an atom is. So if we could look at this one grain of sand, it's a mineral we call feldspar, and we zoom in super close, we could find one giant block of feldspar. And these are all the atoms in it. There's some red oxygens and the orange silicon and the black potassium here. Feldspar is made of 3 elements. An element is a substance that cannot be separated into simpler substances by chemical means. So I can take a substance like water and break it apart into its constituent parts, hydrogen and oxygen. I could take this feldspar and I could break it apart into oxygen and silicon and potassium. Those are substances. An element is the stuff that those are made of. I cannot break down an element by chemical means. I can't put acid on oxygen and try to turn it into something else. I can't light it on fire and expect it to turn into something else. An element is a fixed thing for the most part. There are exceptions. We're not going to get that far. Each element is a unique type of atom. All oxygen atoms are identical for the most part. An oxygen atom is different from a silicon atom, and a silicon atom is different from a potassium atom. They're all unique, but all of the similar ones are the same. So how small is that single atom? If you consider a grain of rice as 0.01 grams, a single grain of rice, you can imagine how heavy a grain of rice is in your hand. You can barely feel it. A hydrogen atom is 1.678 times 10 to the negative 24th grams, or this long chain of zeros. You would never be able to feel that in your hand. It's so unfathomably small. You could fit literally hundreds of millions of them in a grain of rice. So how would we organize all those elements? One of the key things that scientists try to do is organize things. We want to put them into categories so that we can try to figure out, how is this thing different from that thing, and put them into categories. So how would we go ahead and do that? We use something called the periodic table. You've probably seen it before. You may or may not have learned how to read it. It's not as complicated as you first imagine. but it lists all the naturally occurring elements and all the man-made elements. All the elements that could be ever are on this table, and they're separated into two main categories. Non-metals, which are these orange ones, and it's got hydrogen over here on the left, and then starts at boron, and it makes a staircase down the periodic table. Everything over here in that orange is a non-metal. Everything else in these gray colors is a metal. And I like to point out these two rows right here. I have heard every reason why these two rows are removed from the table. They actually belong right in here. This goes from 56 to 71. It actually goes 56, 57, 58, 59, 60, all the way up to 70, and then 71. And then 88 to 89, 90, 91, all the way up to 102. So these are actually down here. This is my favorite question to ask, is why are they down here? I've heard because they're man-made, they're radioactive, all kinds of answers. The truth is, it just wouldn't fit on the page very well. So you could imagine that these two rows belong right in this little section here, and it would stretch out the table, but it would make it really long, and that would make it hard to show on a page. That's the only reason they're removed. The same reason we put Alaska and Hawaii into little bubbles on a map, we put this at the bottom of the table. So let me focus in on just three elements: lithium, sodium, and potassium. Notice that their symbols don't really match. Lithium, Li, that makes sense. Sodium is Na. Well, that's because we found sodium back when Latin was the common language of science, and we called sodium nadium. So that means that when we abbreviated this guy, we just called it Na for nadium. Same thing for potassium. I'm not quite sure what word the K stands for, but it stands for a word in Latin to describe potassium. A lot of the elements do that. They might have a symbol that doesn't really match up with what you think it should. Iron is Fe, gold is Au, silver is Ag. It's because in Latin they sound different. So that's where the symbol comes from. But focusing on just these three in one column, the periodic table organizes elements according to how they combine with other elements. So for instance, here, lithium bonds 2-to-1 with an oxygen. Well, so does sodium. So does potassium. Anything in that first column is going to bond 2-to-1 with oxygen. So, reading the periodic table, there are just a couple pieces of information that you'll find on every periodic table. And these are the only ones I'd expect you to know. The symbol, lithium, is abbreviated Li. Carbon is just abbreviated with a capital C. Anytime the symbol has two letters, the second one will be lowercase. That can get confusing sometimes for some people. For instance, if you have carbon next to oxygen, O, there's also an element, cobalt, that's abbreviated capital C, lowercase o. So you want to make sure that you're paying attention to this case of the letter. If it's lowercase, it belongs with the uppercase letter next to it. And the other thing is the atomic number up here in the top left-hand corner. This number is specific to each element, and we'll get into the reasons why later. But for now, know that every element has its own atomic number. The atomic number starts with hydrogen in the top left and moves across like the words of a sentence to number 2, 3, 4, 5, 6, 7, 8, 9, 10. Just like reading a book. The number increases by 1 as you move across and down the rows. Hydrogen is the lightest atomic element at number 1. Uranium, number 92, is the heaviest naturally occurring element. Everything above 92 has been manufactured in a lab somewhere. We call the rows on the periodic table periods, and we call the columns groups. So this is group 1, group 2, group 3, group 4, because all the ones in the same group share the same chemical properties. The last thing to look for on here is the atomic mass. So we've got the element, symbol, and the atomic number. We also have an atomic mass. And we abbreviate these with a unit called AMUs, an atomic mass unit. It's the weight of one atom of carbon. And it's a 1 AMU is about equal to the weight of one proton. And again, we'll get to why these are decimals and explain this all in a lot more detail later. They're also the number of grams in a mole of that atom. That's a complicated topic, but it bears introduction. We're not going to work with moles in this class. This is very introductory to chemistry. But a mole, think of a dozen eggs. You know how many a dozen is. A dozen is 12. Or a couple is 2. A mole is just a very big number. A mole, if I could skip ahead, is 602 sextillion atoms. The way you might buy eggs by the dozen or donuts by the dozen. You get atoms by the mole. And a mole is 602 sextillion atoms. I include this in here because it's an important number. It's Avogadro's number. And I think it's super impressive to reflect on the fact that this guy, Amedeo Avogadro, figured out how many atoms there were in a mole hundreds of years ago. Think of the amount of technology that he lacked that we have today, and he was able to determine the weight of a single atom. I can't even imagine how he did it. It's fantastic. But it's worth introducing a mole, but we're not going to work with moles in this class. So again, to summarize, matter is separated into mixtures and substances. Physical properties can be seen and measured. Chemical properties are observed when one substance is changed into another. And we arrange the elements on a periodic table with an element symbol and an atomic number and an atomic mass. Okay, that's it for this video. Be sure to watch the second one. I'll post that one at the same time as soon as I figure out how to turn off this screencast.